I'd like to welcome all of you back from Hodge. This afternoon, first of all, will be by Yohan Brunebarbe, and the title is Hyperbolicity in the Presence of Large Local Systems. Thank you very much. So, the goal of my talk will be to discuss some conjecture on hyperbolicity varieties, some conjecture of Green-Griffiths and Lang, and explain that. So, as I will explain, there are different in general, but I'd like to explain that it's some kind of like strong assumption we can stay on. So let me start by explaining this conjectures. So I will, my talk everything will be C, and I will stick to the projective statement. So I start with X, a projective variety, and I will define some subset of X that I want to understand as some different measure of hyperbolicity, depending on the point of view. I will start with the kind of analytic point of view. So I will look at entire curves in X. For this, I define the following holomorphic expression of S. And so by definition, so I look at all image of so holomorphic map and that are non-constant. Okay, so what people usually call entire curve X. And so yeah, and I just do the union. Okay. So I'm creating something, it's a very weird system. Yeah, I don't take that. And another way to define hyperbolicity would be to look at something more algebraic. So for example, the property of being of general type. And so another subset that I will look at the following is the special alge. And I will look at the union of all closed subvarieties, so irreducible closed subvariety, positive dimensional, that are not of general type. So maybe I should say what I mean. So when Y is smooth, so smooth projective, you know, general type considers that the canonical bundle is big. And when it's maybe not smooth, I will just say by definition that it is of general type if any variational model, smooth projective variational model. Okay, so by definition, it is a variational motion. So this is my second subset, and I will define the third one, which is a kind of intermediate subset. So it's like real varieties. And so I will look at the union of images of all rational maps starting from an abelian varieties and with value in X. So it's a rational algebraic map now, and it is a non-constructive. Yeah, so it's a kind of algebraic version of it. And so a small proposition, aside, there are some obvious inclusion. So if you look at this one, it will be included in the one with entire curves, and it is also included in the special locus defined in the canonical bundle. Okay, so I don't forget it's quite easy. And so now I can give a form of the study. So I put conjecture. So this is not the original conjecture. It's even more optimistic form of the conjecture. So it's really in motivated by the Green-Griffiths and the Lang conjecture. So I start as before with X projective. So I will have different statements. So the first one say that in fact these three subsets should be equal. Cool. If this is the case, so I will denote so I will write expression of x for this set. And the second part of the statement is that this subset, which is defined really taking some unions, but really we don't expect anything nice for this subset, but the claim is that it should be Zariski closed. And the third
closure did you write? What closure did you
write? Zariski. Yeah, it's just this also, or maybe I don't know. Yeah, Zariski. Third statement is that so this subset, so this closed subvariety, is not everything if and only if your varieties are general. Okay, so maybe I can comment on what I said at the beginning. Usually, what people call the strong Green-Griffiths and Lang conjecture is they take Zariski closure everywhere here. Okay, so you start with something which is from the beginning of Zariski. What I claim, and I don't know if conjecture is a good word, but at least all the cases which I know, this is the strongest statement is true. And it's, I mean, this kind of statement was explicitly asked in some paper, but not conjecture. And maybe a fourth part, which is maybe the deeper part and the motivation of Lang, is that there is some arithmetic interpretation of this special aside, locus. And so it should be able to recover this locus at the smallest closed subvariety or y in x, such that so each time you take a field, a subfield f of C, which is finitely generated over Q. Okay, so in particular, you could take a number field, but this is of course more general. And I want that my variety x is defined over this field, over which x is defined. Then I can make sense of the f rational point x. Okay, that I did like this. So this is just a set, and I remove the point that belongs to one. And the claim is that the set should be finite. Okay, so the idea of this statement is that so we know that this statement is true in dimension 1. So most of the statements are easy, but this one is very deep, and this is a normal conjecture proof by things. And the goal of Lang was to, at least was to propose a conjecture that could apply to high dimension varieties. And so I'd like to, to give some example where we know that this conjecture is true. So conjectures. So in my talk, I will just discuss, in fact, 1, 2, 3, or it's much more difficult. Maybe do some comments at some point. So conjecture 1, 2, 3 is true in the following examples. So as I said, it's true in dimension 1. And it's an exercise. Okay. So now it's something more general, less easy. It's true for subvarieties or abelian varieties. Yeah, so there have been many work on that. So it started with work of the blog, OPI, Green-Griffiths, for the people, but very studied in the 80s, I guess. And so to give an idea of what kind of result you can expect, so the first result in this for this class of variety that you should start with an abelian variety. And you take X, an irreducible subvariety. Then we have the following equivalence. So X is weakly special. So we saw this notion, I guess, in the algebraic talk and maybe this morning also. And so let me just recall that it means that there is no finite covers that are in the map for positive dimensional general type variety. And so this term would be equivalent to be broadly special. So broadly special means that there is no Zariski length on hierarchical X, and it's equivalent to X is a translate of an abelian subvariety. Yes, so in this situation, we understand very well. So yes, this three so the building piece of this three locus. But so once you know this, so this proves that these three locus are equals. But now the next step is really to prove this and this. And here there are more work. Okay, so another example, which is the generalization of this one, is when you look at varieties that admit finite map.
The surface is 1, 2, 3. No.
For subjective, no.
Because you don't have the density of the action.
No. The 1, 2, 3 for surface of general type. What you need to prove is that if you take a surface of general type, then there should be finitely many rational and elliptic curves, and every entire curve should be degenerate. Okay, and this is not known. We know this from Kelvin by what but yeah, for the cosine
depends on whether C1 square over C2 is more than
exactly. But so it shows that already for surfaces, it's quite intuitive. So deep one. So this is a variety. Varieties that admit a finite map to an abelian variety. And so in view of D, what you really need to prove here is to consider the class where the finite map is a subject. So covers, ramified covers. And this case is it turned out to be much more difficult than this one and was only proved in 2015 by Yohan using an evaluation theory. So something interesting too is that if you look at the conjecture I wrote on the blackboard, so part of it use the analytic structure of text because I look at entire curves, but the part that speak only on the special locus abelian and the algebraic special locus is purely algebraic. So you could try to find a purely algebraic proof of this, and as far as I know, there is no algebraic proof of this. There are a few algebraic proofs of this. I think it would be nice to find one. So another class for which this is known is for if you look at general hypersurfaces in PN, of large degree, very large degree. Okay, and so there were work of Clemens, Fine, Voisin, Brunebarbe, Brunebarbe, many others. And so basically what they prove is that in that case, in fact, what you get is hyperbolic in all the sets. So in that case, all the special locus are empty. So it is for 1 to 3, 4, as far as I know, is open in the so something more related to this conference.
Is there anything known about the locus? Your notion of general, the consequential locus.
This is not really you should ask. I don't think so, but you should ask. So what I know is that Damian found a property which is stronger than hyperbolicity and which is Zariski, and then found maybe Yohan. I don't know. Yeah, so D will be Hodge theoretic, so it's known when it's known when your variety admits a Z, so an integral variation of conjecture with a finite element. Okay, and so in that case, you can also prove that the special loci are all empty. And so in fact, so this is due to the work of Griffiths and Griffiths-Schmidt. To prove this, you need to understand the negative properties of the convention of the periodic. It goes back to the 70s. And so yes, I wanted to finish by saying for surfaces, it's not known that only know like some condition on the term classes, and what is behind is we want to prove, for example, that the cotangent angle is fixed. Okay, so this is some interesting classes for which we use this a lot. And so the result I would like to present is the following. So I take X projective, and my claim is that conjecture 1, 2, 3 are true when X admits a large local system, so large complex local system. And so let me recall what it means. So it's a local system L with the following property, so such that for every each time you take a morphism from a normal and proper variety, which is not constant, then so you can look at the pullback of your local system, and it should be not trivial. Okay, so this is a strong assumption, of course. So one important thing is that if you start with a variety with a local system, then using work of Decidieu and so Decidieu, Katsarkov, Ramatandran, and Pampet on the Shafarevich conjecture. So they prove basically that up to going, if you start with any, let's say, normal projective variety with a local system, then there exists a finite lethal cover and a vibration onto a normal variety with the property that so you first pull back your local system here, and the claim is that it is the pullback of a local system here, which is large. Okay, so up to going to this finite lethal cover, you can always construct the path subvariety. Okay, so I guess this is the best statement you can get if you want to use a local system. Because I remove all the subvariety on which my local system is. And so a remark I wanted to do also is that so I didn't speak about the conjecture 4. And so I'd just like to say that with Marco Maculan, we have some work towards the conjecture 4, so we are very far from conjecture 4. But so what we prove is that when you have a large local system, then if, you can count rational points. And so we prove that the number of points of bounded 8 was sub-polynomial. So in some sense, there are not so many, but quite weak. And so the last remark is that so this statement, the theorem, generalize most of the examples. So it generalizes examples. So A, B, so not C, of course, because hypersubstrate and PM are simply connected, no local system, but in general also. Okay, so maybe let me just comment very quickly on that. So example A, D, so the abelian variety. The remark is that if you take an abelian variety, question?
So you will see what happens. F goes from Y to X. And then you have X prime mapping to Y.
Sorry, it's different. The notation is bad. It's another one. It was my remark on the Shafarevich map. So this is just this is not the statement.
So the statement is that it has F from Y to X.
So here I'm explaining what is a large local system. So it's a local system on X with the property that each time you pull back the local system using a non-constant algebraic map.
But F is not only.
No, it's just
non-constant.
Non-constant. This is what is important. And I put normal, but
So what is the other thing?
this. So this was yes, actually. I remember the statement. And so this is so due to Decidieu Katsarkov, so you start with X So they look at projective smooth, but projective normal works also. And L, the local system from X. And so my claim is that, there exists X prime to X finite data. There exists a vibration from X prime to something that I will call, let's see the Shafarevich. So vibration. And there exists also a locus system from S, a large locus system. Okay, so these three data, such that if you pull back the first one from P prime, is equal to the second one. So the diagram is. Okay, so this was just to say that, so in my statement, I did a large local system. And so, for example, in Yohan talks, he was beginning with a big local system. So, in this situation, if you start with a big local system, it's easy to check that this map has particular action. So, for example, you can treat the case of in the projective case. Here we have the Shafarevich. Not true. Yes, so I wanted to explain why this theorem generalizes most of the examples. So the first thing is the following remark. So if I have A, another variety, then you can just look. We have the map, so the fundamental group is available. And so it's isomorphic to D2G, G is the dimension of the Yohan variety. And so you can just take any kind of representation. For example, you will have a representation like this, so it will give you a local system on A, and this is so this representation corresponds to the local system. It's easy to see that this representation is large. Yeah, okay, so it's an exercise easy to prove using Hodge. And the second remark is that the pullback of a large local system by a finite map is still large. Okay, so this is obvious from the definition. Okay, so using this and this, you recover D and D prime. Another remark is that, so now if I want to recover D, the key point, so my claim is that if a large local system, if a local system underlies the Z variation to the finite map, it is large. And the key point behind this is the following result. So Griffiths in the pure case, and I think Stingring and Zucker in the mixed case. So we say that, so you start with M, the local system, underlying so variation of conjecture V on say X projective smooth. And so the claim is that the local system is trivial if and only if the variation of conjectures Okay, so of course this direction is trivial, and the theorem is this direction. And once you know this result, it's a direct consequence that when you have a finite area map, then you are. Okay? So this is how we prove that D is also contained in this. But this also shows that this theorem deals with more general situation, because here this is true for mixed variation. So you get new examples. Let me new one. This is give new examples. So, for example, F. So I will look at the moduli space of principally polarized varieties. More precisely, the moduli stack, or I should put some bigger structure. And so on it, I have the universal family. And I take X, a variety with a morphism. So X should be projective. And pi should be finite. And so one can see pi as a period map for mixed variation of construction. And so the claim is that X satisfies the conjecture aspect. And so when pi was is a closed immersion, this was already known. But so what is really new is when it's a finite map. And it's as before, so I say, well, it's the difference between D and D pi. There's something to prove. Okay, so maybe I will say something about the proof. I don't know if I wrote theorem 1, so it was theorem 1. So, other questions? Okay, so the yes, maybe first result is the following. So I will fix X, the projective variety, and projective normal variety. And I will assume that it has a large local system. And so the theorem, which is due to work of Campana, Clodon, and Essidieu, and also Yamanoy, so it's two parts of the theorem of the state. So it's as before, so X is weakly special if and only X is broadly special, if and only if X, so up to a finite total cover, X is an abelian variety. Okay, so this is really a generalization of Bloch-Okai type of theorem. Now, I'm only assuming that there exists a large local system variety. Okay, so it's And once you know this means that the special loci that I define are all equal. So in fact, the difficulty to prove the theorem is really to prove what was the statement 2 and 3. I mean, the difficulty. This is difficult, but the new work. So I think that we need to prove that so the following theorem X, so same assumption, X is projective normal and has a large scale. And I need to show that if X is a general type, then the special locus is not that. Okay, so this is really the key step. Okay, so yes, then this is done in several steps. So what you need to do first is to understand the reductive case. Okay, so the reductive case. What do I mean by this? It means when the local system L is symmetrical. And so here the main input is the following. So I start as before with X projective and normal. And I take G over Q bar a simple group. Or G over Q an absolutely simple group. Look at. And I look at the representation of the fundamental group of X inside. So I choose the prime number T, and I look at the representation with value in Q bar. And I ask the following. I want this representation to be large. Okay, so I define this for a C local system, the same definition work for any kind of coefficient. And I want that the image is Zariski dense. And also Zariski dense and also unbounded image. So what do I mean by unbounded? So I look at the natural probability. So in fact, I put bar everywhere, but because the fundamental group is of finite type, I will arrive in some finite extension of P. Not to be clear. And so what is the statement? In this situation, the claim is that we are what we want, meaning that the special loci is not Zariski. And in fact, something important to prove that is that Yaven in his talk spoke of the Shafarevich relation. So starting from the representation like this with value in some theory field, you get some natural vibration. Shafarevich reduction of the X and rho. So it's a vibration in the map. But the claim is that with this assumption, this reduction, this vibration is bound. okay, so the first input. And so I won't give the details to explain how one goes to this, but the basic idea is that if I start with a variety with a very simple local system, then I can look at all the Katar-Kosovo reduction of X for all representation with value in some simple form, in the P, in the QP point of some simple. Okay. So it's infinitely many of them. I do the product. So in fact, this map is factorized to finitely many of them. And the claim is that if you do that, then the fiber on this map, so the fibers, so in restriction to the fibers of this map, and underlined Z TVHS Q. Yes. This is the following result. If you work of Katar-Kosovo sous un résidu. And say that so you start with X projective normal. So G, well, let's say over QP. Reductive. You take the representation of the fundamental group of X with value in the Q point of this G. And so the result is that then there exists a fibration, so meaning a proper map with connective fiber, a surjective proper map with connective fiber. So from X to I write Katar-Kosovo reduction of X4 F such that you have the following properties. So for any map like this with a Y normal, so you can do two things. So first thing is look at the composition Y to X in S, and I say that this is constant. If and only if, when you look at the image of the composition, so pi1 of Y into pi1 of X into G of QP, so this is a subgroup of G of QP, and so this group is the topological group, QP has a topology, and it should be a bounded subset from the group. And it's easy to see that this fibration is in fact unique. Okay. So if I do what I said, then it's clear that in restriction to the fiber, the monodromy, in fact, will be not, but it's easy to see that in restriction of fiber, the monodromy, at least, yeah, I should say normalization. Normalization of fiber, and underline. And I claim that, in fact, so Z local system. And I claim that it underlies will be a variety. Okay, so the semi-simple case will be a kind of they decide between this case, so the theorem that I have here, and the case of variation of field project. But so I'd like to speak also to the general case because this is maybe what is more new. And so this comes from the following thing. When I explain it more the semi-simple case, and there's some, it's not that hard to go from semi-simple to relative. But to go to the general case, I need the following proposition. It's a general statement. So you start with so L, a large local system on X. And so my claim is that we can find the following diagram. So very same kind of diagram that I showed before. So pi is a finite metal. S is a vibration. And such that, so there is such a diagram, such that we have the two following properties. So first, Y admits the large semi-simple local system. The semi-simple local system. And I can say something about the fibers. So the normalization of every fibers of S as a finite and element. Okay, so it might be a bit surprising. So what I said is that in general, to understand any local system, a large local system, you need only to understand to some extent the semi-simple one, and the one, I mean, then the at least the fiber we have the finite one to navigate right. And it's related to the talk by Rodolphe and Frédéric in concept. And so, okay, so now if I know the semi-simple case, what I need to understand is this kind of situation. I understand this, and I want to understand what happened here when I know that this tend to familiar. So I will to go from the semi-simple case to the general case, in view of this theorem, what you need to prove is the following result. So I start with F, any algebraic variety, so maybe not compact. I take A, an abelian scheme on S. I take the finite map from an algebraic variety, so X is maybe not proper. It's the next question. Okay, so this is the following situation. So for if I look at every point in S, and look at the fiber, and the fiber will by restriction it will have a finite map to an abelian variety. And so we are in the situation of Emmanuel method, where we know that the special subset is Zariski closed, and of course it's nice property. And so my claim is that it behaves well in family. So more precisely. So I define the special subset of this map. This is just the union of the special subset of the fibers. Okay, so all these subsets we know by Yamaha result that they are Zariski closed groups, and I claim that this subset is Zariski closed in X. And so when phi is a closed immersion, this is much easier, and it was proved by Napoleon some time ago. But so when it's only a finite map, it's not a consequence of Yamaha networks. In fact, you need to really work Yamaha networks in this setting. And the good thing about that is that this setting is well behaved for some deficit, much more than the setting that Yamaha is looking at. And so even for, if I want to specify this for S point, so I recover, I don't use Yamaha, so I recover with a slightly different group. I mean, it uses a lot of the IDs, but there are some modifications. And so maybe
can you work on AG? Can you
what with this?
Yeah, S is equal to AG. AG.
I mean, so here I don't use the parent map is finite.
No, I understand. Yeah,
I don't know if it was self. Yeah, I don't think so. I don't, because I want the flexibility to the design. Yeah, so the proof is really an elemental theoretic. It's purely analytic, and as I said before, so this statement, if you put SP to be the SP alg or SP ab, it is a purely algebraic statement. And when I is a closed immersion, macular proof is algebraic. And so it would be nice to find algebraic. And so let me finish with this corollary. So I think an interesting corollary of this result is that if you look at the locus, the following locus, we look at the point in S such that the fiber is hyperbolic. So meaning this is empty. And I could also look at, so there is another version where I look at a subset where this is not everything. Okay, so these are two locus in S, and so directly from this, you see that this is Zariski open in S. Okay, so in this situation, this proves that Brody hyperbolicity is Zariski open. So it's well known that without any condition, Brody hyperbolicity is open on the base for different agent consequence of Brody. Very hard. But so here we get 4. And maybe to conclude, so in fact, this kind of statement, the way I wrote it is I really do some kind of relative version of the conjecture. So conjecture, you start with any proper map like this, and so you can make sense of the special locus, and you can be this 1, 2, 3 thing in this relative version. And what I prove is that when I have a finite map to another variety, then you can prove the conjecture of this. And